Hello. Okay, so today I want to try to take on this topic of, no, that's not really centered. Try to take on this topic of Fourier transforms. Um, Fourier transforms are pretty cool. And I've noticed that not a lot of people that I talk to are super familiar with them. So I want to try and build like maybe a more kind of intuitive understanding of the Fourier transform today. So you're already familiar with Fourier transforms, and for those of you who are saying like, oh, why do I care right off the bat, don't worry, you will. Okay, so for example, yeah, sure, let's use this. So now, if I play this thing, this EQ stuff that you're seeing in the back, like the spectrum, that is the result of a Fourier transform of this signal, right? If we zoom in here, we just see this diagram basically that shows us the amplitude over time, right? And on this side, we see this range of frequencies, and we see how much volume there is or power there is in each individual frequency or frequency range or whatever. Now, this isn't usually how EQs are made. They're not usually made with Fourier transforms, and we'll get into like how you make a EQ and blah 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 later. But just so you know that you are already aware of you do already use Fourier transforms. Anytime you can see the spectrum, you can see what frequencies are within a signal, you're seeing the output of a Fourier transform. The other thing that's kind of worth knowing about it is that they come in different sizes. And kind of a fun way to think about this is through the lens of like the Heisenberg uncertainty principle, right? So maybe you've heard about this, that like the more precisely you know the momentum of a particle, the less precisely you can tell its position, and vice versa, right? So the more precisely you can tell its position, the worse you are at telling its of understanding its velocity or momentum or whatever. So, and this kind of is a great intuition for this. So this is like the size of our FFT window, and don't worry, we'll get into all of this in a second. But just so you know, this is a length of time in samples, right? So if you're at 44.1 or 48,000 samples per second, this is a reasonably small. Well, actually, that's a pretty big amount of time. But yeah, and as you decrease the block size, like the window size or whatever, you get less accuracy in this, but you get more accuracy in the time domain. So like it will react faster to changes in the sound. And if you crank it way up, you can see it's a bit slower there. What we're getting is a lot more accuracy in this dimension in the frequency spectrum, and a lot less accuracy in the time domain, because it needs these bigger chunks to show us the spectrum. Okay, so all right, blah blah blah. So now let's get over to here where we're gonna kind of really talk about this. So this stuff here. This is the time domain. So you can imagine this is your waveform, and you can see we've got some kind of lowish frequency, and then it gets a little higher and blah, 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 whatever, right? And after you do the Fourier transform, we get over to this, which is the spectral, or the frequency domain or whatever. So that's like our this display or whatever. And don't worry, it's not only used for visualizing stuff. You can also make really crazy glitch effects with tools that can manipulate the spectrum. So okay, so let's break down quickly how it works. So let's take you know, remember here we had this giant block size of 2048 or whatever, or even higher. We're going to pretend we have a much smaller block size. So we're going to say that we have 512 samples here. What? Hello. Like that. And so what this gives us, is this worth looking up, like how 512, how do you figure this out again? Times, no, divided by 48. So it's like 10 milliseconds at 48K. Anyways, whatever, it's not really that important. So if we take our 512 samples, then what we're going to get out is 512 individual bins in the frequency domain. Now, for people out there who know a lot about working with Fourier transforms, shut up. Yes, we're going to pretend that you put in 512 and you get 512 out for now. We'll get to the other stuff later. Don't worry about that. Okay, so we take our 512 samples in the time domain, right? This is a graph, and the axes are amplitude over time. And here our axes are power over frequency, right? So these are the lowest frequencies, and as we go up, we get higher and higher frequencies. And that's what it's going to show us. And the cool thing about Fourier transforms is that you can actually do them the other way around. You can flip them back around and turn them back into a signal. Now, every time you do this, you're adding latency, right? So here we need to have a full buffer of 512 samples. So we add 512 samples of delay. And 512 samples is not a very big FFT window, so it probably won't sound super great. Okay, so so that's cool. Now, you know, you might be wondering, well, what kind of stuff can you do with the Fourier transform? Like, why do I care about Fourier transforms? And actually, before that, you might be wondering, so is this how, you know, I know we already mentioned this, but no, this isn't how EQs are made. It's not really how a lot of things are made, but it is an important component in a bunch of effects that I think are really fun and exciting, and we're sort of going to talk about them a little bit. So, well, we'll see how much time this takes, but whatever. Anyway, so, okay, so what do we use this for? So whenever you see spectral in the name of something, it means that it's using some sort of Fourier transform sort of stuff. So most of these effects are made in a different way. It's mostly like delays and some sort of like distortion or whatever. Mostly, we're not going to get caught in the weeds in that just yet. But you see something like this, spectral blur, for example. I don't know how to use this thing, but oh yeah, there we go. So here you can see our spectrum. This is obviously a pretty small FFT window. So you can get these kind of blurry effects. You can get even cooler than that. We'll get into that more. This is a spectral resonator, so I'm assuming this is sort of like an additive resynthesis sort of thing. Also very interesting. And here you can see 256 harmonics. So this is relating to the window size or whatever. Okay, so and then we have a bunch of cool effects that we can do. And the cool thing about Fourier transforms is they're sort of unintuitive when you're first learning about them, right? So I mean, hopefully I'm explaining it in such a way that you're like, oh yeah, this makes sense. But you know, maybe not. So they can do a bunch of cool stuff. It looks like there's not very many effects in here. I don't know how that's made. Okay, so whatever. So let's dive into Max now. Now, okay, so let's just bring this over here. Oh, that looks pretty small, so maybe we'll make it a little bit bigger. Okay, so we're up to the 10-minute mark. So maybe I'll end it here for this one, and in a second we'll have, the next video in the series will be how to use the Fourier transform in Max. Hello, this is a video, the continuation of a video about the Fourier transform. And we're going to build a Fourier transform in Max, and hopefully that will help us sort of understand what we can do with it, what kind of weird stuff it does. So, okay. So in Max, there's like a couple ways of doing Fourier transforms. And I'm just going to use this super basic one, even though it's not really the best way to do it. But just because it's kind of easier to see what's going on and stuff. So, okay. So we take our I think this is the best way to do this, but okay, whatever. So we take our signal going in, and maybe we'll even do like divided by 2, divided by tilde 2. So we'll take a mono sum and then we'll divide it by 2. So we're doing a mono thing here. And now, right. So now there's these 3 outputs. And this can look a little bit daunting. So I don't know if you can read that, so I'm just going to read it out to you. So the first output is saying the real output. And the second one is saying the imaginary output. And the third one is saying the ramp from 0 to number of points minus 1. Okay, so that sounds kind of confusing, so let's go back here. Okay, so when you do this, I guess the first thing, we'll just get it out of the way. What is the number of points or whatever? What they're talking about is the number of samples, and we use those as the bin index. So that number that's coming out of there, it's going to just be shooting out 0, 1, 2, 512, 0, 512. And it's just going through these really fast at sample rate, right? And it's just telling us like, okay, what's coming out of the real and imaginary, the first 2 ones, is going to be the value for this one, and then the value for this one, and then the value for this one, and then it's telling us which one is there. And that got deleted. Okay, cool. Okay, so that's cool. Now, what's the deal with this real and imaginary blah blah? So, Fourier transforms deal with this thing called complex numbers. Now, we don't this is not super critical for understanding Fourier transforms, but it's really fucking cool. So we can I guess we'll kind of talk about it a bit. So what are complex numbers? Basically, you have let's go like this. So you have your let's try to draw a straighter line maybe. Okay. Thank you, Google. You won't make it smaller? All right. Fuck you. Okay, I'll try and draw a straight line here. All right, so you've got your real number line, right? So you've got 0 in the middle, and then you've got 1, 2, 3, blah, blah, blah. Let's put some dots. 1, 2, 3, 4, 5. And then over here, you've got the negative numbers. 1, 2, 3, 4, 5. We've got negative 5 here. I don't know why I choose 5. It's just kind of random. Okay, so imaginary numbers or complex numbers were come up with, or they came up with them, or both, I guess, imaginary and complex numbers, came up with to answer the question, oh shit, I hope I don't get this wrong now. What is the square root of 1? God, I hope I got that right. It's like 1 or negative 1. Anyways, it's not that important. But whatever. So the idea is, and you know, this is going to sound weird, blah, blah, blah. It's going to sound kind of made up, but it's not made up. And actually, there's a lot of really cool uses like the Fourier transform. So don't get scared. You don't have to understand this fully. Just let the information gloss over you, blow through your hair or whatever. Okay, so the imaginary numbers is the idea that these are our real numbers, right? So we have like 5 apples or I guess these ones kind of don't really make any sense either. You can't have like negative 5 apples, but whatever. So we're kind of playing with this idea of like these things can be useful, right? And so what we're doing in the complex plane, or the imaginary numbers are just numbers that go in this direction. 1, 2, 3, and 1, 2, 3. And if we just put like 3 here and negative 3 here, it would get pretty confusing, right? Because we don't know which 3 we're talking about, right? Are we here? Are we here? Where are we? So the little convention that they used is just to, if you're talking about imaginary numbers, you just put an I afterwards. And the I doesn't do anything. It's just like a notation thing. It just says like, okay, these numbers are in the up and down direction. They're not over here, right? So the square root of 1 is I. And so, okay, so, all right, we're getting pretty in the weeds here. So I don't want to, I don't want to get too carried away, but this stuff is really cool and really interesting. And there's, maybe I'll link a 3 blue 1 brown video in the description. Maybe some other resources about this if you're curious about the math and you want to get more into it, because it's really weird and interesting. Okay, so enough of this square root blah blah shit. So when we do our Fourier transform, and this has to do with the underlying math, Euler's formula, blah blah blah, it's some mathy stuff, which again, check the description if you want to get more in the details of that. But here we're thinking about music, right? So so what we care about is that the Fourier transform, when it does its thing, it's going to poop out a bunch of, it's going to poop out a bunch of these kind of complex numbers, right? So we're going to get a big kind of smattering. I don't know where they usually land, so I'm just kind of drawing them wherever. So we get this kind of smattering of these real and imaginary numbers. Now, these are not super helpful to us by themselves. There's not a ton that we can do that I'm aware of with these by themselves. But you can do this cool thing where you take that real and imaginary number and you pretend it's just an xy coordinate, right? Like we're pretending here. And then what we can do is we can transform it from the Cartesian plane, which is this xy yada yada, right? So your Cartesian, so this in Cartesian coordinates would be 1, comma, I, right? So that's your Cartesian coordinate. You can translate this into a polar coordinate. And what that means is that we get 2 different numbers. Instead of x and y, we get the length of this part, so the magnitude, and we get the phase, which I think is from this axis. So we get this angle. This is getting a little bit hard to see. Hopefully it's not too bad. So we get, so we get this angle here, and we get this magnitude, like this length here. So say if it was this point, then this would be our length, and all the way this would be our angle. And the cool thing about that is, and I hope you're still with me because this is where it gets fun. So the cool thing about that is that each one of those refers to the amplitude and phase of a component sine wave of this thing. So what we're doing is we're taking this and we're basically comparing like a sine wave that goes like this, right? And it's like, oh, okay, so that one's in there, right? Because we got a bit of it. And so we say, in this bin, we have, it's not super loud, but we've got a bit of this frequency sine wave, right? So let's say it's 10 hertz or something, I don't know, or 1 hertz, right? So we have like a bit of 1 hertz, right? And then we also have this other window that looks like this. I don't know why I didn't draw this before. We have another window that looks like this. This is the same, but these little lines in here are indicating the phase. And this one usually, God, I'm so bad at fucking drawing. Whatever. So yeah, these ones indicate the phase of their partner, right? So we have a sine wave at 1 hertz with a phase of I don't know, 0, I guess. I don't know. And then we have a sine wave at 2 hertz, and that one has different phase. So the phases maybe, the phases are usually between negative pi and pi. So you can kind of convert that into degrees or whatever. So it's like between negative 180 degrees and 180 degrees. Anyways, we'll get to that in a second. So that's kind of the crux of it. That's like the imaginary numbers stuff. But so again, super importantly, we don't really care about this math stuff. It's fun. It's really interesting to learn, and I hope that you do go and learn about it because it's awesome. But for all intents and purposes, like for all our synthesis and resynthesis and manipulation needs, we don't give a shit about this. Like it's not really that important. What we care about is after we do that thing, that we know that what these bars mean is this is the volume of this frequency, and this one is the phase of that frequency. And we also know that if we add all these waves together, if we generate 512 sine waves with these phases, we're going to get this back. Okay? Okay. See you next time.